Hello, welcome to this video. Today we're going to evaluate this sum. So I have the sum as k goes from 1 to n minus 1 of 1 over sine squared of pi k over n. So let's begin. So what I want to do is try to find a nicer way to write 1 over sine squared. Mainly as sum, maybe infinite sum or infinite product, something that'll make this easier to evaluate. Because right now, even if we try to turn this complex, maybe use e to the theta I with sine, try to get that formula, maybe get to some, maybe get to a geometric series that we may be able to evaluate. I tried it, it doesn't really work. So that's what we'll do instead. So we'll recall from a previous video, which was about the Basel problem. I'll link it in the description. We found that sine x can be written like this: x times the product of n the natural numbers, 1 minus x squared over pi squared n squared. And where that came from was trying to express sine x as a product of x minus its roots, and then times some constant, and then after plugging that in, we got this is true. So what I want to do is expand this into 1 minus x over pi n and 1 times 1 plus x over pi n, because that's the difference of squares. And then I'll have both n and minus n, so I'll be able to write, instead of n the natural numbers, n in the whole numbers except 0. Because if we had 1, 2, 3 all the way on to infinity, now we also have the negative of each of those. We'll have 1 negative, 1, 2 negatives, and so on to infinity, negative infinity. So it's going to be all the whole numbers except 0. Right, so let's write out slowly. We have x times product, then was the natural number over the natural numbers, 1 minus x over n pi, 1 plus x over n pi. And now, like I said, I'm going to change the order of multiplication inside this infinite product, such that now I'll be going over all n that are in the whole numbers except 0, and then I'll only do the product over this term. So this is going to be x times the product, and in z except 0, this little star means it's z. It's just the whole numbers except 0 time of x over n pi. So this is equal to sine x. Now what I want to do is take the natural log of both sides. So I have natural log of sine x, because I want to somehow deal with an infinite product, and the only actual way for us to do that here, to get somewhere, will be taking the natural log to turn us into an infinite sum, which we have much more tools to deal with it rather than infinite products. So natural log of sine x is natural log of x plus, right, the product here turns to a sum, and this infinite product turns to an infinite sum. And then zx at 0 of natural log 1 plus x over n pi. And now, this natural log is really bothering us. It's like everywhere it's ugly and it's really annoying to deal with. So what we're going to do is take the derivative of both sides to get rid of it. So we'll have the derivative of natural log sine x is the derivative of sine divided by sine. So that is cosine divided by sine, which is just cotangent. That is equal to the derivative of natural log x, 1 over x, and the derivative of this, so we can take the derivative inside of the sum. And then, so we first of all have this at the bottom, and then we have the derivative of this at the top, which is just going to be 1 over n pi. This is 1 over x plus the sum over n, that's whole numbers except 0, 1 over x plus n pi. And now notice that if we plug in n equals 0, we just get 1 over x. So altogether, this is the sum just over the whole numbers of 1 over x plus n pi. So now this is just in z, so all the whole numbers. So now we found this. And now, I just want to take the derivative once again, because we know the derivative of cotangent is negative 1 over sine squared. And then we'll be able to have, and then getting rid of the negative, we'll be able to get an infinite sum representation for sine on this side. So we'll take the derivative. So we have negative 1 over sine squared x is equal to, again, we take the derivative inside the sum, and the derivative of 1 over x plus n pi will be negative 1 over x plus n pi squared. So we get take the derivative again, we take this. And now both of these have minus signs. Oh, we can take the minus sign outside of the sum and then just get rid of it on both sides. So we found that 1 over sine squared x has this infinite sum representation. The sum as n goes, as the sum as n goes over all the whole numbers, 1 over x plus n pi squared. So let's quickly erase this, write this identity again, and then we'll go on evaluating this sum. Okay, now that we found this identity earlier, let's evaluate this sum. So, of course, I'm going to rewrite 1 over sine squared as this infinite sum. So, let's write this. We're going to have the sum. This k goes from 1 to n minus 1. And then the sum, so of course I'm not going to use n in the sum, as it's already being used. So I'll use m. 1 over, we have pi m plus pi k over n all squared. So now I'll take pi over n, I'll take 1 over pi over n squared outside of the entire brackets, because n is a constant and pi is a constant. So now I'll turn it into n squared divided by pi squared. And we'll be left with, so the pi will go away, and this n will be multiplied by n. So I'll have the sum. Scale goes from 1 to n minus 1. The sum as n goes over the whole numbers. 1 over k plus m times n squared. Okay, now let's think about what this sum actually is. So we're summing over 1 over whole numbers squared, and here basically what we have is like going over all the numbers that are not divisible by n, right? Because each number that's not divisible by n, it could have, after dividing by n, it could have a remainder of 1, of 2, all the way up to n minus 1. And this is represented by this k. And so we'll exactly sum over k plus m times n when k is the remainder, and then m is just what's left for you to get to that exact number. So this is basically summing over all the numbers that are not divisible by n of 1 over that number squared. Right? So let's actually write this. N squared over pi squared times the sum of I such that n does not divide into I, 1 over I squared. Keep in mind it's not the imaginary number, and I squared is -1, I is just an index. Okay, so what I want to do is add and subtract a nice term such that we'll be able to actually evaluate this, because this looks very close to the Basel problem, which is just summing over 1 over I squared when I is a natural number. And that's a famous result of pi squared over 6. We actually proved it in that video of the Basel problem that I mentioned earlier. But what I want to do is add and subtract the sum over all the integers I that are not 0 and that n does divide into them. Of course inside the brackets, right? Of n squared over pi squared. So this is going to be something like this. So now, summing over all the numbers that are not divisible by n and that are divisible by n except 0 is just the sum over all integers except 0. Okay, so this turns into the sum over all integers I that are not 0. So there's that z star again, of 1 over I squared. Then remember, we're subtracting the sum over the integers, not the non-zero integers that are divisible by n. So that's just like writing n times a non-zero integer. So that's the sum over I is n z star 1 over n times I squared. So this n times I is that non-zero integer that's divisible by n. So now we can take 1 over n squared out of the brackets here, and we get 1 minus 1 over n squared times this sum. So we have n squared over pi squared times 1 minus 1 over n squared times this sum. But we'll notice that this sum is actually, this 1 over I squared is equal to 1 over negative I squared. So instead of summing over all the non-zero integers, we can combine the same terms, which are I and negative I, and get to the sum over I. It's a natural number of 2 over I squared. So this is going to be times the sum of I and the natural numbers of 2 over I squared. But now, n squared times this thing is n squared minus 1 divided by pi squared times 2 is 2 times the sum of 1 over I squared as I goes over the natural numbers. That's exactly the Basel problem, which is, like mentioned earlier, is famous to known as pi squared over 6. So now we have that's pi squared canceling out, 2 cancel the 6 to give us a 3, and we end up with the final result of n squared minus 1 over 3, which to me is a bit unexpected from the sum, but that's the result. And finally, that's it. If you want more content like this, please subscribe to my channel. I'll be uploading more interesting content and things like this in the future. And finally, that's it.